Today's my lecture topic is multi-stage rockets. In multi-stage, once the concept has been suggested, it is easy to see intuitively that in discarding at least the empty fuel tanks during the flight is bound to improve the performance of a rocket. The thrust remains the same, but after the tank have been topped off, the mass of the rocket is smaller, so the acceleration will be greater. To calculate the effect, one can consider a rocket of given mass ratio and then divide it into two smaller rockets whose combined mass is the same. The payload, or that part which is to be put into orbit, is the same in both cases. This means that for a fair the test we need to separate the payload mass from the structural mass. The mass ratio of the single rocket can be defined as R naught equal to ms plus mf plus fp divided by ms plus mp. This is the same definition but with the structural mass separated out. Note that here is the convenient to use mf as the propellant or fuel mass to distinguish it from mp. The payload mass, the structural mass will include the mass of the engine, turbo pumps and fuel tanks, as well as the guidance and control electronics and so on. Since in general we may expect that the structural mass will be kept to a minimum, we many reasonably assume that it is a constant fraction of the fuel mass for stages using the same fuel. The rocket is then divided into two rockets, each having half the fuel and stacked one on top of the other. The first rocket is ignited and burns until all its fuel is exhausted. This gives the whole stack a velocity. Define the rocket equation. Here the mass of the fuel burned is half the single rocket fuel load. The lower rocket then drops off and the upper rocket is signed. It then gains additional velocity defined by the rocket equation. Here the upper rocket begins its burn with half the structural mass and half the fuel mass, and ends with half the structural mass and payload. The final velocity will be the sum of the velocity increments produced by the two rockets. So to compare the performance of a single and two-stage rocket, we have to compare the following. The advantage of two-stage approach will be related. For example calculation, we assumed a rocket total mass. This corresponds to the mass ratio, and if the rocket is divided into two smaller ones, here the velocity increment is close to that of the single stage rocket. The final velocity is then of V1 and V2. Therefore, using the same quantity of fuel and dividing the structural mass between two smaller rockets, the mass ratio of course even smaller, but this time there are three rockets to share the load. The steps the same for two rockets, the fuel and the structural mass being shared equally amongst the three rocket stages. The total velocity achieved by the three-stage rocket is 8092. So the extra stage has improved the velocity by another thing. Optimizing a multi-stage rocket is, for example, they given above some assumes it can be by means of the calculus of variation that for equal exhaust velocities under the same propellants. The optimum velocity increment occurs when the payload ratios of the stages are equal. If the structural efficiency of the stages is the same, this is the equivalent to declaring that the mass ratio should be equal. The payload ratio of a single stage is given by L equal to mp by ms plus mf. If it is also convenient in the payload ratio, L is the ratio of the mass of the payload to the mass of the rest of the rocket. The structural coefficient sigma is the ratio of the structural mass to the combined mass of the propellant and the structure. Thank you.